Hello everybody, my name is Pascal Nicolay. I'm R&D Project Manager at CTR, Carinthian Tech Research, which is a research center located in the southwest of Austria, close to Italy and Slovenia. First of all, I would like to thank the organizers of the ECSA 5 symposium for the very kind invitation to give this keynote. And I of course also would like to thank you for watching this video. So here are the outlines of the talk. I will start with a short presentation of our activities here at CTR, and I will then tell you about the basics of surface acoustic wave technology and surface acoustic wave sensors. I will then focus on a new emerging field for SO sensors, which is SO sensors for structural health monitoring applications. After that, my colleague, Nicolay will tell you more about his own activities here, that is magnetic sensors and systems for industrial applications. So, CTR, the Carinthian Tech Research, is a non-profit organization which was founded 20 years ago. It is funded at 50% by the Austrian government, the 50 remaining percent being provided by our industrial partners. We have currently about 60 employees, 14 PhD students, and we have a turnover of about 7 million euros per year. We also have a lot of collaboration with universities, and you can see here a short list of our main academic partners. At CTR, we have three main kinds of projects. In the first one, we have the European funded projects and the nationally funded projects. So I guess you are all familiar with some of the names you see here. In the second category, we have the so-called COMET projects. So the COMET program is a funding initiative of the Austrian government, which is managed by the FFG. And CTR got the COMET label many years ago. So we are COMET Center, and we get budget to carry on R&D projects with our main partners, our main industrial partners. And there is a third category of projects here, and here we have the fully paid project. So our customers, our partners, they come to us with specific requirements, and we develop specific solutions for them, and they pay 100% of the project costs. At CTR, we have four main areas, so microsystem technology, photonic sensor systems, smart systems, and packaging and heterointegration. We also have a brand new clean room, and you can see here some of the machines and equipments we have in the clean room. And we are going in the following weeks and months to develop processes, MEMS devices, MEMS sensors, actuators, etc. for various kind of applications. So for more information about what we do here and what we could do together in the frame of collaboration projects, for instance, please feel free to contact directly Thomas Ladstätter and Heimo Müller. They are our sales representatives here. We can now switch to the first of the two main scientific topics of this talk, SO technology and SO sensors. First of all, what is a SO sensors? You probably all know that we can have in materials two kinds of propagating acoustic waves. You can see them here. So on the left, you have a longitudinal wave. On the right, you have a shear wave. Under certain circumstances, these two kinds of waves can combine and give birth to a third kind of waves, which are guided at the surface. Here you can see one of the most famous ones, which is called a Rayleigh wave, after Lord Rayleigh, who first described it theoretically in 1885. So in the case of a Rayleigh wave, the energy is confined close to the surface, and the penetration depth is of the order of 1 wavelength. So now, if your material is piezoelectric, you have inside a direct coupling between the between the electrical and mechanical fields, which means that if you deposit two metal fingers on top of your surface and you connect these metal fingers to a voltage source, you will be able, thanks to the piezoelectric effect, to convert your electrical signals into mechanical signals. That is, in our case, into propagating mechanical waves. Now, if you use only one pair of fingers, it won't be enough to generate a big enough signal. So you need many pairs playing together, so interacting constructively to generate a big enough signal. And this combination of pairs is called an interdigital transducer, or IDT. It was first invented in 1965. So by using such an IDT, you can generate much bigger signals, and you can see here on this picture, which was taken using electron microscopy, the impulse response of such an IDT. So this picture was taken by engineers from Siemens many years ago in Munich. One typical parameter for SAW devices is the frequency, and the frequency is, like always, given by the ratio between velocity and wavelengths. But in our case, the wavelength is directly fixed by the distance between two consecutive pairs of fingers. So some typical values. For a surface acoustic wave device operating at 1 GHz, a typical value for the wavelength is 4 micrometers, which also means that the typical finger width is 1 micrometer. So we are talking about micrometers here, which means that to fabricate these devices, you need to use the microfabrication techniques, which are usually used to fabricate MEMS or computer chips. You can see here, for instance, one of the main equipment you need to fabricate such devices. In the middle, in the bottom of this slide, this is a stepper, okay, a high-end stepper. On the left, you have a series of blank wafers, and on the right, the final state. So you can see here zoom of one of the metal fingers. Now, how can you sense with a SAW sensor? So you know that the frequency is given by the ratio between velocity and wavelengths. But the velocity depends on material parameters like stiffness constants, piezoelectric constants, density, and also permittivity constants. So each external perturbation that will change or affect one of these material parameters or device parameters will have an effect on the frequency and or on the propagation time. So by tracking frequency and or propagation time, you will be able to deduce the amplitude of this external perturbation. I have 3 quick examples for you. So mass sensor, strain gauge, and temperature sensor. In the case of a mass sensor, if you have on top of your device a thin absorbing layer, the density of the thin absorbing layer will change with time when the gas molecules just get absorbed. In the case of the strain gauge, you will stretch your material, and this will generate changes in your stiffness constants, density, propagation lengths, and also you will have inside some stress fields. In the case of the temperature sensor, you will heat it up, so you will change the material parameters, the stiffness, and the material might become softer. You will also change its density, and this will of course also have a direct effect on the frequency. So you can see here that what happens in 3 different cases. What are the parameters which are changed by either mass or strain or temperature, and all of these parameters have a direct effect on the frequency and or on the propagation time. Now, what's really interesting with SAW sensors is that they can be wirelessly interrogated. How can you do that? So there are 2 main ways to do that. First, you can use so-called resonators. So here your IDT is located between 2 reflector gratings, which define a resonant cavity. And if you connect your IDT to an antenna, instead of connecting it through wires to your voltage source, you will be able this time to convert radio frequency signals into acoustic waves and acoustic waves back into radio frequency signals. Okay? So now how can you interrogate your sensor? You have two ways to do this. First, you can use frequency sweeps, so you can send different frequencies and you can check the response of your resonator, and you will see that when your interrogation frequency is tuned and to the resonator frequency, you will have a maximum in the response, and you can track the evolution of this maximum versus temperature or strain or absorbed mass. A second way to interrogate these devices is to load them, so to load the resonator, for instance over 30 microseconds, and then to switch everything off and to listen to the response, to the decay. And you can Fourier transform the decay and again extract the resonance frequency of your sensor so that you can again follow versus or track versus pressure, temperature, strain, etc. The second way to interrogate these devices is to use so-called RF tags. So how do they work? Here you have an IDT, you send a pulse, and the pulse is going to be converted into mechanical waves, and these waves are reflected back by reflectors and converted again into RF signals. So you send a pulse and you get a few pulses back. So the position in time of the echoes will of course depend again on the perturbations you want to measure. But that's not all. Here you can also see that you have a sequence of peaks. You have 3 peaks in our case, 1, 1, 1. And there is a missing peak, for instance, which is 0 at the end. You could have 4 reflectors and you would get 4 peaks. Or you could change the space between the reflectors and change the space between the peaks, etc. So this is kind of a barcode. And this is something you can very easily use to identify which sensor just responded to you. So this is the technology we use here at CTR. So these RFID tags, you can see here schematics about our own system. So we have a reader unit, we send pulses, we get pulses back, and we infer from this response temperature information or strain information and ID. You can see here a comparison between simulated and experimental results for one typical temperature sensor with 3 peaks. So now it's for sure important to know when and why you should think about using a source sensor. So first of all, the source sensors are quite sensitive. You can expect for mass detection a sensitivity close to 200 ppm per micrograms per square centimeters, so on your surface. For strain sensors, you can expect maximum sensitivity or typical sensitivity of 1 ppm per microstrain. And for temperature, your sensitivity can be as high as 90 ppm per Kelvin, which means, for instance, that if you are using a 1 GHz source sensor, you will get up to 90 kHz variation per Kelvin, which also means that you can get very accurate in temperature. In our case, we can, depending on the algorithm you use and also on the fact that you can or not use averaging techniques, you will be between 1/10 to 1/100 of a Kelvin in final accuracy. So, as a reminder, source sensors are very small. They are easy to manufacture and they are cheap. Source sensors are passive elements. There is no battery and no electronics. That's why they are intrinsically so robust. And that's why they can operate in harsh environment, for instance, up to temperatures equal to 350 degrees C. So this is kind of a lookup table for you to use if you are thinking about using source sensors for applications. First of all, do you need something wireless? If yes, source sensors might be one solution among others, and maybe not the best one if you are just looking for wireless devices. Now, if you have to operate without embedded electronics, without battery, then source sensors are becoming one of the few possible solutions. Now, if you also have to deal with extreme environments, so high temperatures, up to 350 degrees C, high pressure, high voltage, high radiation level, corrosive environment, then you almost have no other choice than using surface acoustic wave devices. And if on it, you need the identification functionality, then you really should think about using surface acoustic wave RFID devices. And just to let you know, we work essentially in the past for the steel industry, for the automotive industry, and for the aerospace industry. And this was almost always about providing solutions for monitoring in extreme environment. So now, what about structural health monitoring? The first application we are thinking about is to implant those sensors for monitoring strain. So implantable strain sensors. You can see here one of our sensors mounted in a TO39 standard housing. It's 1 centimeter in diameter. And here you can see the whole system. So we have a CTR reader connected to its antenna. And on this red plate, you can see one source sensor connected to a big metal, very robust antenna. And we are thinking about using this system to monitor bridges, so strain states in bridges, in tunnels, on airplane parts, etc. To show you what happens when you mount such a device on a deformable blade. This is what we did here. So we mounted the sensor, we glued it on a strain blade, and we checked what happens versus applied strain. So you can see on the right that the sensitivity is very linear in a very wide strain range, from 0 to 1000 ppm. You can also see that the sensitivity changes with the angle. This is due to the anisotropy of the crystal, and it also shows that you can somehow use this anisotropy to adjust the sensitivity of your device according, for instance, to the application you are targeting. A second application we are thinking about is to implant temperature sensors in various kinds of materials. You can see here a collection of our SAW devices, different shapes for the housings, but they are all more or less 1 centimeter in diameter or in length, and the antennas are quarter wave antennas, dipole antennas made to operate at 2.45 gigahertz, so they are a few centimeters in length. We first checked that we can implant our SAW devices in glass fiber reinforced polymer resins and still interrogate them through this material. And this was very successful. We managed to implant these devices, to embed them in the resin and interrogate them up to a distance of 15 to 20 centimeters. We also, for one application, had to embed our SAW devices by injection molding in liquid crystal polymer. So here the requirements were for the targeted application was identification of drill pipes on the rig and during transport, and the requirements were 250 degrees C, 1300 bar, operation abrasive liquid, so the sensors had to be chemically resistant and temperature stable. And they worked very well. But we can already foresee main limitations for this technology. The first one is due to the fact that we are interrogating wirelessly at high frequency, in our case at 2.45 gigahertz. So this means that we won't be able to go even through very thin sheets of conductive metal. And this can be a blocking point. We also checked that we unfortunately cannot go interrogate our sensors through even thin parts made of carbon fiber material. Okay, so we don't go through because the carbon fibers are also conductive. Another problem we probably will have to face is housing failure, because if we want to implant SAW devices in materials, they will have to withstand the process conditions, which means high temperature, pressure, and so on, chemicals all around. And one possible solution might be to simply get rid of the package. So I'm going now to tell you just a bit about a new concept we have, and this concept is to use so-called packageless sensors. So here you don't use surface acoustic waves anymore, which are sensitive to surface states, but you use guided bulk waves. In this case, I'm showing you on the screen, you are using a multi-layer structure made of ALN, zinc oxide, and lithium niobate, and you are guiding waves in the zinc oxide layer because the zinc oxide layer has an acoustic impedance which is much lower than the acoustic impedance of the two other layers. And as the wave energy is confined in this thin layer far from the surface, your device becomes surface insensitive. Okay, so if you also think about embedding the antenna in your multi-layer structure, you might end up with this kind of device. You can see here on the fingertip. So this one is an actual SAW device, but without guided waves and without antenna. But at the end, we might obtain this kind of device with antenna inside and guided waves, and you could just take it in your between your fingers or implant it wherever you want. This is the goal, and we hope to be able to develop this kind of solutions within 3 to 5 years. Thank you very much again for your attention, and please do not hesitate to contact me if you have questions about SAW devices and sensors for structural health monitoring applications. Goodbye.
Finally, in the last part of this presentation, I would like to talk about magnetic sensors and systems for industrial applications. My name is Michael Ortner, and I've been working in this field in the past 5 years with multiple industrial partners. Magnetic sensors measure the magnetic field. They have been around for a long time, and there are now many established sensing technologies, each with their advantages and disadvantages. In the graphic on the right-hand side, you see the resolutions of different established sensing technologies. And depending on what you need in the application, you have to pick the one that is right for you. Industrial applications require specific features like low cost and high reliability. Today there are multiple industrial sensors available based on different sensing technologies and designated for different applications. Integrated versions of the above technologies have been realized for Hall sensors, for magnetoresistive sensors, and quite recently also for flux gates. When you have high magnetic field applications with magnetic fields of the order of 50 to 100 millitesla, then you will typically want to use a Hall sensor. If you want to measure around the Earth's magnetic field, meaning in the 50 microtesla range, then you will probably use a magnetoresistive or a flux gate sensor. In this talk, I want to specifically focus on magnetic position and orientation detection for industrial applications. In the graphic on the bottom right-hand side, you will see a sketch for such a system where a permanent magnet which generates a magnetic field moves relative to a magnetic field sensor. From the modulation of the magnetic field detected by the sensor, one can calculate the relative motion between the two. In this case, the resolution depends, of course, on the amplitude of the magnetic field. So you will typically want to focus on high magnetic field strengths and use Hall sensors for this purpose. Such systems are quite well liked in the industry due to their excellent features with respect to reliability, long-term stability, the ability to function in dirty and greasy environments in machinery without the requirement for environmental protection, the low cost, and also the low power supply. One specific example for magnetic position orientation detection is linear position detection, as it is used, for example, in a gas pedal. When you press the pedal, a magnet moves along a linear path in X direction, as it is indicated in the graphic on the right hand side. And a sensor is placed in a distance from it. Now the sensor detects the longitudinal and the transversal components of the fields, and those components are indicated in the graphic on the right hand side by red and blue lines. You will see that one component is even and the other component is odd, and there is a very smart way by taking the ratio of one component over the other component to create a tangent-like function, and by applying an arctangent to create a linear relationship between the output of the sensor and the position of the magnet. In modern cars, there are today more than 100 applications for such magnetic sensor systems. They include, for example, wheel speed sensing and ABS, where you detect the rotation of the wheels of the car, for gas pedals, brake pedals, for the steering wheel angle, for any kind of current measurement, and of course also for the gear shift, possibly also for the side mirrors, for throttle position, camshaft position, crankshaft, and many other applications. The linear position scheme that I have shown above is quite simple. But in general, when an arbitrary motion, rotation and translation should be mapped magnetically, possibly with mechanical constraints within a machine or ferromagnetic surroundings, or with requirements on external stray field stability, this design of the magnet sensor arrangement can become quite a difficult task. We refer to this as magnetic system design, and it is laid out in the graphic on the right hand side. We have a given system and observables of interest, for example, the motion of a gear shift system. Magnetic system design is then done in two highly interrelated steps. First, one must find a concept for a magnetic map. This means that one must find a concept for a one-to-one correspondence between the magnetic field, which is the signal output of the sensors, and the observables of interest. The second step is referred to as magnetic field shaping. Once a concept exists, magnetic field shaping is just an optimization problem. How to arrange sources and sensors in an optimal way to achieve the best results in terms of resolution and stability. Magnetic system design is a complex task, and there are many ways to address this problem. We are mainly working with geometric shape variation methods, where multivariate optimization is used for field shaping. This works really well with fast analytical solutions that can always be established when there are no soft magnetic parts around. Finally, this is the case most of the time. It is almost a critical requirement not to have such parts, as they enhance external stray fields and make them inhomogeneous, and therefore impossible to eliminate by differential measurement. At this point, we are a few weeks before uploading our Python-based magnetic toolbox for magnetic system design termed MagPy to GitHub if you are interested in this. An alternative approach for field shaping is solving the inverse problem. However, in both cases, geometric shape variation and solving the inverse problem, one must first know the magnetic map, and at this point there is no established scheme to find it. Let me finish this presentation by showing you some examples of previous works with magnetic system design that we have done over the years. In the first example that you see at the bottom of this slide, we have arranged off-the-shelf magnets in a string to enhance the range in a linear position detection system. This is the same application as the gas pedal that I showed before, but by arranging the magnets smartly and by using the third field component, we are able to enhance the range as is shown in the figure on the bottom right. In fact, we were able to achieve a factor of 2 in terms of range while keeping the total magnet volume the same. This is interesting because of what I mentioned in the beginning. Cost is a critical factor for industrial applications, and rare earth materials that are used for neodymium or samarium cobalt magnets is an expensive resource, and you always want to minimize this. Finally, on the last slide, I want to show yet another interesting example. In cooperation with the University of Vienna, we have printed permanent magnets with variable magnetization amplitudes. The printing technology was actually established by Christian Huber, who is a former student of Professor Süß from the University of Vienna. In the upper left graphics, you can see a magnetic filament where magnetic particles are integrated into a polymer matrix that is then used for printing. And the variable filling fraction is realized by arbitrary mixing of the magnetic filament with a non-magnetic one during the printing process. This allows us to establish an arbitrary magnetization locally. And in the upper right hand corner, you see the resulting printed magnet. The idea here was to vary the magnet filling fraction in each printed layer to generate a magnetic field with a perfectly linear component along the magnet. The application here would again be linear position detection, like a gas pedal or something similar, but only to use a 1D sensor, which is again much cheaper than a 3D sensor, for example, in order to determine the field. The theoretical calculations are shown in the bottom left figure. In orange you see the field of the designed magnet, while in blue you see the field that you would get without such a variable magnetization. And you can see that the designed magnet has a really nice linear component. On the right hand side you can see the experimental results, and they are quite in good agreement with the theory, but of course this technology is still in its initial stages, and perfect filling fractions are difficult to achieve at this point, but it shows the viability and the potential of this method. With this, I would like to end my introduction to magnetic system design for industrial applications. I hope you find the results interesting, and I will be happy to answer any questions. Thank you very much for your attention.